Welcome to this video in which we are going to discuss a common phenomenon in sample signals, which is called aliasing. In 1928, Harry Nyquist proved that when an analog signal is converted to a time-discrete signal, the sample frequency has to be at least twice the highest frequency of the analog signal in order to reproduce this signal without errors, and that is shown in this video. Let's have a look to this signal. We have a sine wave over here, and that sine wave is sampled at certain points. Here, 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 etc. And we see that in this case, we do not meet the requirement of Nyquist. So the sample frequency is not twice the frequency of my sine over here. And then we see what happens, because when we connect all these sample points with each other, we see that we get a new signal over here which does not meet the original sampled signal anymore. So we can't reproduce the original signal anymore. So this picture shows that you have to meet the requirement of Nyquist, so that the sample frequency has to be at least twice the highest frequency of this signal, so the signal frequency over here, to be able to reconstruct the original signal. Otherwise, it isn't possible anymore. And you see that in a lot of situations, for instance, on TV or in movies, in which cars start to rotate in the wrong directions. But also, this movie is a very interesting one. You see what happens to the rotor of this helicopter. Well, it seems that this rotor isn't moving anymore because the frame rate of the video, which is the sample frequency in this case, is equal to the rotor frequency. So, yeah, it's really quite interesting that in this case the helicopter seems to move without rotating the rotor. So that is caused by aliasing. Well, let's have another view to this problem. Let's look from a frequency point of view. So I'm going to look in frequency domain to the spectrum of a signal. So suppose this is my signal in the frequency domain, which could be my voice or something like that. And my maximum frequency is omega h over here. And we have also a negative omega h because of the math to get this picture over here. And we're going to sample this signal, and what happens is the following. This is my original spectrum, and what we see is that that original spectrum also pops up at the sampling frequency, but also at twice the sampling frequency, at minus the sample frequency, minus twice the sample frequency, etc. So it pops up at another places in this frequency spectrum. And the width of this spectrum is, of course, the same thing. It's still omega h. So this is in our sampled signal, the frequency content of that signal. But when we want to filter out and reconstruct that original spectrum, we have to filter out this part of that spectrum, because in that case we have the original signal back. But that is only possible when this point, omega s minus omega h, is larger than this point. So when omega s minus omega h is smaller than omega h, then we have a combination of this spectrum and that spectrum, and we are not able to filter out the original signal anymore, because this is what happens in that case when omega s is smaller than twice the maximum signal frequency omega h. It's not possible to filter out that original spectrum. So we have to meet the requirement that the sample frequency, omega s in this case, has to be at least twice the maximum frequency of my signal. Otherwise we get aliasing. And we have used a ideal filter over here with a really steep curve, which is infinite in this case. So in practice, the sample frequency has to be, let's say, 5 to 10 times the maximum frequency of my signal. And what we see in motion control situations, motion control problems, that we choose a sample frequency which is at least 10 to 20 times the maximum signal frequency or the maximum bandwidth in that case. Then we have another problem, and that is this case. In this situation, we have noise around the sample frequency. And when we have noise around the sample frequency and we start to sample this signal, we see that the noise is also popping up in all these frequencies which we get back due to the sampling. So we have also low frequency noise in my original frequency. And to get rid of that noise, there are two possibilities. First of all, you can increase the sample frequency. That is a possibility, and a commonly used solution is that you filter the signal before you start sampling. Well, that is all about aliasing. Thank you for watching, and I'll see you next time.